For this video, we are going to focus on confidence intervals about a population mean. If you haven't seen the video on constructing confidence intervals about a population proportion, you should do that because it has a lot of necessary information with diagrams and so on, and it's explained in much more detail. For these problems, we're pretty much going to go through them quickly. They're very similar to the population proportion type of confidence intervals problems because basically we just find something called E, and we have a formula for it, and then we subtract E from something, and then on the other side we add E to something. So let's take a look at this problem 5. It says a particular Yanmar sailboat diesel engine specifications sheet claims that the engine can run for 10,000 hours with proper maintenance before a major rebuild becomes necessary. A survey was conducted on 65 randomly selected, well-maintained sailboat Yanmar engines of this type, and it was determined that the mean number of runtime hours before a rebuild became necessary was 9,320 hours. It is also known that the population standard deviation of runtime hours before a rebuild becomes necessary is 1,162 hours. With a 90% level of confidence, construct a confidence interval about the population mean number of hours necessary before a rebuild. That's supposed to say is necessary for this particular Yanmar engine. And then there's a second part to this. Does the 10,000 hours stated on the specs make sense? So I'll explain how we answer that after we get the confidence interval. Just like the population proportion type of problems, we first need to determine the correct sampling distribution. Since this is a problem for which we're asked to determine the confidence interval for a mean, we have a decision to make. In order to make that decision, the question we need to ask is sigma known? Meaning, are we given a population standard deviation in the problem? The answer to that for this problem is yes. It says right here, it is known that the population standard deviation, etc., is 1,162 hours. So we're given a population standard deviation. Since the answer to that question is yes, the correct sampling distribution is the standard normal, just like the population proportion problems. If the answer was no to that, we'll talk about it later, but we use the T distribution. It's actually called the student's T distribution, but we just abbreviate it as the T distribution. For this problem, we need to determine the following parameters. X bar, which is the sample mean for the problem, either sigma or S. So either the population standard deviation or the sample standard deviation. N, which is the number of measurements used, the number of people surveyed, number of engines in this case that are surveyed. A level of confidence, and just like everything else, if there's no level of confidence or level of significance given in the problem, then we default to 95%. This problem, they explicitly give us a confidence level right here, a 90% level of confidence, so we don't have to resort to the default. Okay, alpha, or the level of significance, and it's the complement of the level of confidence. Alpha over 2, just like before, self-explanatory. we divide the level of significance into two tails. Z sub alpha over 2. This is the exact same thing we used when we did population proportion confidence intervals as well. We use the norm.s.inv function. Nu, that's what this symbol is. This is Greek. This is the Greek letter nu, the lowercase Greek letter nu. And we use it to represent something we call degrees of freedom. I just love that. The calculation for nu is very simple. Nu is simply the number of measurements we have minus 1. In other words, for this problem, it says that 65 randomly selected, well-maintained sailboats. So that means that N is 65, but nu, or my degrees of freedom, is 64. It's that simple. And we also have this thing, if it's necessary to use it, if we're given S, or if we have to calculate S or approximate the standard deviation, then we find T sub alpha over 2. And again, this problem, we're given the population standard deviation, so we don't have to worry about the T sub alpha over 2. If we did, however, we would use the t.inv.2t alpha comma nu function, and we'll get to that. For this problem, then, we have x bar, or the sample mean, is 9,320. Sigma is equal to 1,162, and it's given to us. It's not S, it's a population standard deviation. N equals 65. My level of confidence is 0.90. Alpha is 0.10 because it's 1 minus my level of confidence. Alpha over 2 is just half of alpha. As it looks, it's 0.05. And I'll tell you Z sub alpha over 2 in a case like this is 1.645. The E formula is either, if sigma is given, it will be E equals Z sub alpha over 2 times sigma over the square root of n. A pretty simple one. Or, if sigma is not given, but we have a way of approximating it through S or another method, E would equal T sub alpha over 2 times S over the square root of n. So for this particular problem, E is equal to 1.645 times 1,162 over 65, which is approximately equal to 237.07. That's E. So once you get that, just like in the population proportion confidence interval problems, this becomes just a simple subtraction and then an addition. We take that E and we subtract it from x bar, and we say is less than or equal to mu, or my population mean, which is less than or equal to x bar plus E. Again, for this problem, that means we have 9,320 minus 237 is less than mu, which is less than 9,320 plus 237.07. And that basically means that mu falls somewhere between 9,083-ish and 9,557. To answer the second part of this, does it make sense that the rebuild would be necessary after about 10,000 hours? And the answer to that is really no. And the reason why is, with a 90% level of confidence we can say that my population mean, mu, is between this 9082 or 3 number and 9557. If 10,000 had been in there, in other words, if this went from 9082 to 10,150 or something like that, then we could be 90% confident that that 10,000 would fall somewhere in there and they would be correct on the spec sheet. So if I go back up, I'll explain a little bit more what I mean. On the spec sheet, it said that it could run for 10,000 hours with proper maintenance before a major rebuild. But 10,000 hours does not fall in this range. That being said, it's close. And, what's the difference between, 9,500 and 10,000? It's just 500 hours. But it's still probably an improper thing to put on a spec sheet if it doesn't even fall in a 90% confidence interval. Let's go to spreadsheet mode and see what this all looks like on a spreadsheet. Here I have the spreadsheet set up. We have X bar equals 9,320. N is equal to 65. For this value, new, which we don't need for this particular problem, but we'll put it there just to make it more user-friendly so that we can use this for either if sigma is known or sigma is not known. As you can see here, I have this whole panel right here. If sigma is known, then we just look at this one and it'll do the correct calculation. If sigma is not known, it will automatically populate this area. I'll explain that again when we get to a problem when sigma is not known. But it's an easy calculation. We might as well just put it in. So this will equal n minus 1. And again, that's the calculation for new, otherwise known as our degrees of freedom. S, or sigma, is 1,162. That, again, is just given to us in the problem, and it is given to us as sigma. My level of confidence, 0.90. Alpha, well, that equals 1 minus, and we're going to always let our spreadsheet do that kind of work for us, so we only populate it with specific parameters. Alpha over 2, well, that equals alpha divided by 2. For this panel, right here, the one in greenish, we will say equals for sigma, and I'm just going to click on the cell that contains that. And again, I will explain this to you later and why I have it set up this way. It just makes this spreadsheet a more multi-purpose spreadsheet. We have z sub alpha over 2, and if you remember from last video, that equals norm.s.inv of alpha over 2. And it's going to give me the negative result. So I'm going to do that little trick I did last time and nest this within an absolute value. So it equals absolute value of norm.s.inv. I have an open parenthesis for the norm.s.inv function, close parenthesis for that. And now I'm going to close my parenthesis for the absolute value. And as I had shown on the problem sheet, that works out to be 1.645. And now we do our E calculation. The E calculation, if you remember, was sigma is known, z sub alpha over 2 times sigma over the square root of n. And one of the beautiful things about that is that the order of operations is pretty easy on that. It will automatically take that into account if you just type it in exactly that way. So we would type in equals z sub alpha over 2 times sigma, which I'm going to get from right here, over SQRT of n, enter. And there you see it, that 237.07, just like on the problem sheet. Now all I have to do is subtract this number from x bar on the left side of this, and take this and add it to x bar on the right side. So this is going to equal x bar minus that 237.07 number, and over here equals x bar plus that 237.07 number. And again, the meaning behind this is we can be 90% confident that the true population mean would fall somewhere between 9082.93 and 9557.07.